today we're gonna get to see the big breakthrough in like 10 years ago, but it's still really cool, and which is basically approximate Mach flow, but only in undirected graph, but in almost linear time. Okay, and today we will not use push level for once, but next week we will use it again. Today we're gonna use something called multiplicative weight update, and I just gonna state the black box, and if you are interested, you can look into it. Yeah. But okay, that's the goal today, and we see how to do it. Okay. It might be that I don't finish today, and we continue tomorrow. Okay, so let's start with like basic terminology again. So for today, I just gonna call flow in quite liberal way. Flow today is it still capture what flow is, but it's just like a function that I like that for any u and v which is not an edge is still 0. So basically just still assign value to two edges, and but like here we think like we have this thing, the flow from u to v is basically a negative of flow from v to u. Okay, so like okay, this is just the flow. Yeah. And the congestion is as we expect. So just look at overall edges, maximize overall edges, the value of the flow over the capacity of an edge. Okay. And if the congestion is at most 1, we say that the flow is feasible. Feasible means the congestion is at most 1. It respects the capacity. Okay. And the net flow, just like before, is just the total flow out of the net flow out of u is just the total flow out of u. The inflow into u just contribute negatively to this term. Okay, so that's normal. And like instead of talking about separated source, 1 second. Yeah, instead of talking separately about source and sink function, we don't want to do this. Like it's kind of less convenient today to talk separately about source and sink. What I'm gonna do is just kind of combine it into one function. Like it's more convenient today to just consider a single function, and it's just a source minus sink. Like the source part contribute positively to this function, the sink part contribute negatively to this function. Okay, so formally I just say that I formalize it like as a function that map vertices to some number can be positive or negative, and I call this a vertex demand if the sum is 0. So basically think like you have a graph, and maybe I put +1 here, +2 here, and -3 here. This just means like I have source 1, source 2 here, and I want to send to this sink. Okay, just that's the intuition, and it should sum to 0. If it doesn't sum to 0, then there is going to be some remaining unit that cannot be sent. So this thing should sum to 0. Okay, and I said that the flow F route this demand D if like the flow out of at any node is like the net flow out of node U is just exactly the demand D at the D of U. Okay, so if, for example, if this is -1, then like a path like this, where I put value 1 on if every edge here is just the flow that routes this demand. And the demand is routable if there is a flow that routing it. Okay, and you see like why I need this, right? Because if the total demand is non-zero, then it's just impossible to route. Okay, and then here's the next terminology. The residual demand. Okay. The residual demand D after routing F is defined like this. For every node V, the residual demand at V is the original demand minus what we have been routed out of V. So dF is just D minus F out. And okay, and we said that D respect a node weighting A if like absolute value of D is at most A on every node U. So all this is just like kind of the notion that we are familiar with, but I just like repeat everything in terms of this function D. Any questions about this? Okay. And okay. And here is the, okay. Now I also gonna write D of subset S as a total demand inside S. Things can cancel, right? If this is +1 minus 2, then this D of S is -1. Okay. Now you can confirm, like try to prove this yourself too, but that the demand is routable with congestion 1 if and only if for every vertex set S, the total demand in S is at most the cut size. Okay. So one direction is clear. Like if there is some cut S such that, let's say the cut size is 10, but the demand, like maybe the total demand here is like plus 30 minus 10. So you kind of, it just means that like no matter what, you need to send out of this 20 units. But there are only like a 10 unit of capacity to go out of the set. So there is no way to send it with low congestion, with congestion 1. Okay. But it's true too that like actually if for every set here, when you sum it up, then the total demand in here is at most the cut size. If this is true, then you know actually that the demand is routable. Okay. You can try to prove this just using Maxwell mean cut theorem. I won't prove it for you. It's just, yeah. Okay. Okay. So now, so basically now the problem of approximate max flow is as follows. You have a graph, capacitated graph with capacity C and some this vertex demand D. Okay. So what I want to do is just like two cases. This approximate max flow problem, I use this as a subroutine for this problem. Route in G, route D with slack epsilon. Okay. So what it does is either output a cut such that the cut size is less than the total demand inside it. What does this mean? it's just a certificate which says that you cannot route with congestion 1. Okay. This just really means that there's no way to route with congestion 1, just from theorem 1. Otherwise, if this is false for all cuts, it means that actually there is a way to route feasibly. There is a way to route D with congestion 1. But we have some slack here instead. We just need to find some flow routing this demand with congestion 1 plus epsilon. So that's approximate MAC flow problem. So if you use if epsilon is 0, you can see that just by using MAC flow black box, you can actually solve this problem when epsilon is 0. But this is the problem we want to do today. Okay, so now when you are okay with really big approximation like M, instead of epsilon being 0.1, let's say this epsilon is big like M, number of edges, really bad approximation. Okay, then they claim that you can solve this just by using maximum spanning tree. Okay, I might talk about it tomorrow if I have time. But this actually I still didn't publish the homework, but this is in the homework actually. Yeah, but yeah. So take it for granted today that if you want really bad approximation, then you can do it in linear time already. But the goal today is to get, instead of M approximation, you get 1 plus epsilon. Okay. Now, this is a problem, but we're gonna look at another related problem. Okay. It looks a bit more relaxed. Is this problem? It's a problem where, again, you have a same graph of demand. And this problem is epsilon almost route, which is you get the same input, but this almost route does the following. It either output the same cut, the certificate that, let's call it violating cut, is the cut which says that the demand is not routable with congestion 1. This is the same cut. But otherwise, it's going to return a flow. This flow will have congestion 1. It's feasible flow. But what I say is that what this guarantee is that the residual demand is routable with congestion epsilon. Okay. What does this mean? It means that there exists another flow, let's call it flow augmentation, that if you add it into your flow, then think like this augmentation as the flow that route the residual demand. Okay? And when you route this residual demand, you add it to your flow, and this will now route the whole demand. And this in total will have congestion at most 1 plus epsilon, because F aug will have congestion just epsilon, and F has congestion 1. So together it has congestion 1 plus epsilon. So you see the connection, this thing, route D with congestion 1 plus epsilon, similar to this one. Okay? But it just said, what we return is just F, and we said that there exists some way to augment it so that it routes the demand exactly with congestion 1 plus epsilon. For example, I might I might do this. Let's say this is like plus 100. I might just actually just send flow. So that like this is plus 1, plus 1, plus 1. This is minus 1, minus 1, minus 1. Like my flow might not even reach each other at all. But the residual flow now looks like just only plus 1 here and minus 1 here. And like suppose that this residual demand is this thing. And it promises that the residual demand, it's like easy to route with low congestion, with super low congestion, with congestion just epsilon. Is the problem clear? Right now I just need to understand the problem definition. Okay. So it's two different problems. And like this one is less standard for sure, like because it doesn't really route your demand. It just promises you that there is a way to augment it so that it routes your demand. Okay. But so like the route subroutine is more standard. Okay. But actually they are basically equivalent. Okay. Okay. So the first one, if you have a subroutine for the first one, you can solve the second one here easily actually, just by making like one calls to the second one. Like you can implement almost route just by calling route once and just do some scaling. I will leave this as exercise again. Okay. The idea is just call route and then scale it down. That's it. Why it works, you can think about it. Okay. So the idea is like you call route, which basically route D with some congestion, and just scale it down by 1 plus epsilon, so that now it's feasible. But it will route, if you scale it down to this route, just D over 1 plus epsilon, but it's feasible. It has congestion 1. Now like, what would be F awk? F awk would be just like F minus this thing. Okay. And F awk would have low congestion. Anyway, yeah, it's something like this. It's just easier. This is easier problem. Like almost route is easier. But what we will do, I will show you actually that you can implement route by using almost route too. Okay. So if you want to solve route, maybe with like slack to epsilon, you can solve almost route by making like log n calls. Basically, small number of calls. Okay. And some small additional time. Maybe m log n. Actually, yeah. Okay. And the algorithm is just this. So the goal, like, once we see this, we're gonna see like how to solve almost route. Okay. For now, like, let's see that how to solve route using almost route. Okay. So the first step is I just gonna call almost route. To solve route, I just call almost route subroutine. And well, if it returns a cut, then it's the same cut that we want, so we are done. But otherwise, this guy will return a flow, a feasible flow. Okay. Let's call this F0. And then I just gonna say that like look at the residual demand of F0, which we know that it can be routed with congestion really low, like epsilon. Okay. Call this D1. Now we're gonna loop, maybe. Yeah. Okay. I'm gonna make loop log n rounds. And what I'm gonna do is to call almost route. Maybe let's look at the first round. The first route is just this. It's just gonna be calling almost route in epsilon g d1 epsilon. Basically, I call this thing. Okay. This is the first loop in this for loop. Okay. I'm gonna try to route d1 in G after scaling down capacity by epsilon. Okay. So this thing might return a cut or flow. But can it return a cut? I claim no. Because we know that this demand is routable in epsilon G, right? It's just from our promise. If it's routable, then there is no way that you can find a violating cut. So it's just gonna return a flow. Okay. So this is like you basically try to route this residual demand D1 using this flow. Okay. So that's like you get F1, and then you define D2 to be residual demand. To be residual demand of F1. So this one is residual demand of F1. What do we know about this? This demand is routable with congestion epsilon in which graph?
Epsilon squared?
Yeah, it's routable with epsilon congestion in epsilon G graph. So it means that it's routable in G with congestion epsilon square. Okay. And you keep going. Like first, like you have like things are routable. Like the residual demand is routable with epsilon. Next round, the residual demand is routable with epsilon square congestion, and it just keep going down exponentially. Okay. Good. And after log n round, then like this residual demand, like the last residual demand will be routable with congestion like really tiny, like 1 over poly m. Okay. So what we're gonna do is just we're gonna route this residual demand in this graph, which we know that like this residual demand can be routed admit this congestion epsilon to the k plus 1, and we can maybe now route with like big congestion, like m here, like this thing is going to be something like 1 over m to the 10 or something. It's super tiny, so even if we pay congestion a bit more by m, doesn't matter anymore. And how do we do this? It's the exercise that I omit, right? The one that use maximum spanning tree. So let's assume we can do this. Okay. So what we need to return is just the sum of all this flow. The first flow route something and left with some residual demand. The second flow route the residual demand and left with like even tinier residual demand and so on. And the last one is just kind of to like take care of the rest that is super tiny. Okay. Does this make sense? Okay, so I hope you see that. Like, yeah, I just basically explained to you that the almost route like for every I, this guy will return a flow because it cannot return a cut. Okay. Yeah, basically di is routable in G times epsilon to the I. Okay. I'm gonna skip this proof. Okay. I hope you are convinced. Right. And so now to conclude, how did we solve route? Okay. With slack to epsilon. So except the last guy, we know that like f is feasible. Yeah, fi is almost route of epsilon ig di epsilon, right? So it's feasible in this graph. So it has conjugation epsilon to the I in G, which means that this sum, the flow that we return, will have conjugation 1 plus epsilon square plus so on up to epsilon to the k. But then the last guy, instead of having epsilon to the k plus 1, you pay m because we use the crude approximation. Okay. And this sum in total, if you set epsilon to be like maybe like less than 1/4 or 1/2, you get this thing. So now, like the conjugation is just 1 plus 2 epsilon in G. And F will route D exactly. And that's super intuitive, right? Because we just keep finding some flow and we get residual demand. We find a flow that route this residual demand and get another residual demand and so on. And the last guy will just route the smallest residual demand. Okay. So we route all the demand. Okay. So I hope now you're convinced that like now the goal is just to solve almost route. Question up to this? Okay, and we're gonna solve almost route using multiplicative weight update. I'm gonna tell you what this thing is, and once we see what this is, we're gonna solve the problem on expander first, and then generalize to general graph, like same template. Okay, so let me tell you about weight update. Okay. This algorithm. This is like, you think of it as a framework. MWU, multiplicative weight update. It's just extremely powerful, flexible, appears everywhere. Okay. Yeah, I really encourage you to learn this, but for this class, we're just gonna state the theorem. Okay. And it works like this. So the theorem is that you're gonna have some indices, set of indices J. Think like you have J many choice, okay? And there's some parameter, doesn't matter for now. Okay. Initially, like for each index, I just initialize my weight to be all 1. And there's gonna be some loop. Okay? Think of this loop as something tiny, like log n round. You should think like of omega here as 2, and alpha here is maybe something like epsilon. So this is going to be like log n over epsilon square. Okay. Not too many rounds. Okay. And in each round, what do? What will happen is this. Just compute this distribution. This is what it is. It's just a weight scaled down by the sum of the weights. So it's just a normalized weight, basically. Think like you can think of this as distribution over indices too, right? You have some weight, Like for example, in the beginning, this is all 1. Then this is going to be uniform distribution in the beginning. Okay. And okay. Then some adversary, which you have no control of, will choose a gain vector. Okay. So which is just assign some number to each index. And this gain will certify, but this is arbitrary gain vector, but it certifies some property. First, the absolute value on every vertex, on every index. This is just, a max J absolute value. Yeah. This is infinity norm, okay, which is just this thing. So every index of G of the gain is at most omega, or at least minus omega. It doesn't go like too far off from omega. Think of this as 2 for now. And then what does this say? This thing is just inner product, which is the sum of Gj, Pj, right? Or if you think of this, if you think of P as a distribution, we can think like expectation of J when you choose J according to P. Okay. You can interpret this in many ways. Okay. But the point is that its inner product is small. It's bounded by some value. So think like when you choose index, right now you just think like inner product is small. Or like okay. And then what happened is that once this happened, what we're going to do is just update the weight on each index according to the gain. How? If on index J the gain is big, then like increase the weight by like this thing. Okay. If the gain is negative, this would decrease the weight. Okay. So note again that this thing is just, maybe you can forget this thing for a bit, but it's just this thing is basically 1 plus, it's the same thing, right? So if G is positive, then you kind of increase multiplicatively to the weight. If G at like index J, the gain at index J is negative, then you decrease it multiplicatively. So the weights of each index kind of increase multiplicatively or decrease multiplicatively according to the gain. Okay. And at the end, we will promise that the gain, like the average gain vector, what is this? This is just the average of the gain vector. Okay. Will be such that for every single index of the average gain vector, this is small. Okay. So if this is a kind of small on average, then at the end, this thing is small in worst case. Okay. So right now, it might be hard to interpret this. I'm gonna interpret this for you now. Okay. Okay. So let me give some interpretation. So imagine that you want to choose a stock, like which stock to buy. Okay. There are many stocks in the stock market. Okay. And on day T, you might choose one stock J. Okay. If you choose a stock J, then at the end of the day, you know the result, and you're gonna gain this money or you lose money, depending on how big this thing is. The gain vector is just something that they reveal to you after you choose. So if you choose stock J, you gain GJ at day T. Okay. If you choose instead a distribution, not just one index, not just one stock, you choose this distribution over indices, then you gain this much. This is just an expected gain. Okay. Okay. And the most important point is that in this scenario is that the gain vector is revealed after you choose P. Okay. Like this, like you kind of fix your how you choose the distribution first, and then some adversary just choose the gain vector. So like this gain vector can even depend on P. Okay. All right. Okay. This is a kind of scenario that you should think of. But what do we like guarantee? What this thing says, like basically we have no regret. In what sense? We have no regret in the sense that suppose that our gain on each day, like suppose that you choose distribution PT, this is how we choose stock on each day. This is then GT inner product with PT is just the expected gain per day, right? Suppose that what we gain is at most is small. Let's say like it's smaller than some value on every day. Then, if we look back, like suppose that like after T days, and then we look back to the past, and then we look at the best stock J. Okay. Like let J be the best index when we look back after T days. So what is this J? It's just the stock that maximizes the total gain. Okay. This is just the one that maximizes this thing. Or I write it like average over T days. Okay. Then what we guarantee is that this one, the average gain of this best stock per day is not going to be much more than what we get. It just guarantees that this thing is at most val plus something small. Okay. So what does it mean? It means that even if we knew the best choice, like even after T days, after all the days that we have, we know the best choice, which is maybe like some J that maximizes the total gain. Even if we know the best choice, we wouldn't gain too much more. Because this gain per day for even the best stock is at most val plus something tiny. But we gain per day, we gain like this at most val, but even the best guy gain at most val plus alpha. So basically no regret in this sense. Okay. So let me go back. Okay. Again, right? We start with some like imagine that you want to choose a distribution over indices. And how I gonna choose distribution over indices is to just choose it according to my weights. And as long as I update my weights multiplicatively, I update the weight multiplicatively. I use this MWU step here. As long as I do this, then if the gain per day is smaller than value, then when you, after T many days, when you look back and look at even the best stock, this guy will gain not much more than what you gain per day. Questions about this? Yeah.
Could you explain in the interpretation, what do you mean by like look back when we select the J index?
Yeah, so like if you look at this thing, right? What is this thing?
It's the average across all rounds, basically.
Yeah, basically this, like, you look at this is defined only after T days. So I look back to like through the
period.
Yeah, I look back from day T, look back to day 1, and look at the gain that each stock gain per, like for every stock, how much does it gain? Okay. This is just the average gain for each stock. And then I said that even the best stock will not gain much more than what you get. Right? Because what you get is basically kind of val, you get at most val per day.
Each, yeah.
And then like even the best stock will not gain much more than what you get per day. Okay. So basically, like, this is one algorithm to invest, for example. Yeah. Like just like update the weight according to the gain multiplicatively, and you gonna guarantee that you have no regret in this sense. Okay. Questions? All right. By the way, note that like the comparison is just slightly unfair. Why? Because we can choose distribution of indices, and we can change this on every day, but we compare ourselves with just one fixed index. But anyway, this is an interpretation. Okay. So keep this in mind. Okay. That we can kind of turn this, if we can keep this in mind. Yeah. Okay. Now we're gonna see how to use this for solving almost route. Okay, just recall again, almost route, we have a graph in D and epsilon. We either find a violating cut or find a flow whose residual demand is routable with congestion epsilon. Okay. And let's try to solve this problem on expander first. Okay. So on expander, just recall that if G is a phi expander, it means that the node weighting degree is phi expanding in G. That's what it means. So in particular, any demand if D respect phi, then D is routable, right? Just like definition of expander. And okay, what we're going to show is that on a file expander, we can solve almost route in this time. So if phi is not too small, then this is near linear time. Yeah, and the core idea is just that if the demand respects epsilon phi degree, then this demand is routable with congestion epsilon. That's the core idea. It's just like something that we are so familiar with. But like, so now the strategy is then we're gonna get an algorithm that either return a violating cut or return a flow such that the residual demand respect epsilon phi degree. If we can do this, then we are done, right? Okay. So now here's the algorithm. So first of all, like the first step is just a trivial step. I just first check that the demand on every node doesn't exceed the degree. Because if it exceeds, if the degree is 2, but demand is 3, then there's no way to route feasibly. You can just return this as your evaluating cut. So just ensure this first, just a trivial step. And then initialize the weight. Okay. So for every node U, I have 2 weights. The weight at U plus and the weight at U minus. Weight U plus, weight U minus. And there is like a day on each route for each day t. So I initialize the weight to be 1, just like in MWU. Just note again that each node has 2 weights. And then what we do is this. There's going to be like this number, some number of rounds. Okay. And first, I just compute the potential. It's going to be like the weight plus minus the weight minus. And scale it down by degree. In the beginning, in the first round, this is just 0, right? Because the weight is just all 1. And then we're going to construct the flow for each route t. What does it say? This is just some formula, but what we do is just to flow at full capacity from higher to lower potential vertices. So basically, what is this potential? It's just basically kind of put all vertices into a line, right? Potential of node U, this is like a put it at this position. V is just at this position. So every node is in a one line. And what we do is just for every edge, if this is an edge from U and V, then we're just gonna send, and suppose that this is small, this is big. Okay? Then we just send flow at full capacity. If the capacity here is 3, just send flow 3 from V to U. Actually, let me draw it like this. Let's say this is negative, this is positive. Yeah. And then I just send flow. Yeah. So large potential is here. Actually, no. Let me just draw it like number line. Yeah. Small potential is here, large potential is here, and just send flow at full capacity. If the potential are different, just send flow to from higher to lower. Yeah. So from higher potential to lower potential. Okay. Is this clear? This step is clear, right? Just on every edge, just do this independently from everything else. Okay. And now if now we're gonna look at like residual demand and multiply, like it will look, take an inner product with the potential. You don't need to understand this yet. If this thing is small, then what we're gonna do is to update the weights. Okay. How? Like we compute this relative excess at U. Why? Like this is like excess at U, right? This is residual demand at U. So basically like excess at U, but I scale it down by degree. So every node computed this relative excess. It can be positive or negative. If it's positive, there is excess. If it's negative, there is deficit. Then like I just update the weight. So for the weight plus, if there is excess, then the weight will increase. Okay. If the excess is a lot, then this guy will increase a lot. And weight minus is basically it's gonna increase if there is deficit. If there is a lot of deficit, it will increase a lot. Okay. Okay. Otherwise, if this is actually big, then I claim that there is a way to fire a violating cut. Okay. I will describe this later. But you should think like that this is kind of a bit intuitive. Why? Like it's like I put this thing, just put like what is this into number line, right? And maybe like 0 is here. Okay. And if this thing is positive, then it means that like, so this is like this is number line according to phi, all right? And let's say this is positive part, this is negative part. And this is gonna be positive or big if maybe like, if all the positive guy have a lot of residual demand, residual excess, like a lot of excess here. And this guy maybe have a lot of deficit. So if basically, you know, like, if this is the case, then like there is a lot of excess on the same side and a lot of deficit on the same side. So like it looks like you can fire a cut where like there are a lot of excess need to be sent. So that's why there should be a violating cut. Yeah.
Is it kind of a similar thing that we did when we were proving the flow cut gap?
Similar, yeah. You're gonna see the proof, and it's gonna be quite similar. Yeah. Okay, this is just intuition. You're gonna see clearly why you can get violating cut soon. But for now, just assume that this doesn't happen, and we focus on the third step. And at the end, we just return average flow. Okay. What average flow? Just like to take each flow on each day, average them. Okay. So let's analyze the running time. You can summarize the algorithm again. Like I just first compute potential. That is just like ON time, right? The potential, maybe I just do this, yeah. This thing just takes ON time, yeah. And then this just OM. It's really simple here, just look at each edge, which one is like higher potential. Yeah. And this one, you can compute in ON, just inner product. This one, ON as well. That's it. Like it's clearly linear time per round. So the total time is like there are this many rounds, and alpha is epsilon phi. So this is the total time. So that's clear. Just need to see why it's correct. But before that, let's see why it's super intuitive actually. What's going on right here is actually, and this is kind of intuitive algorithm. So what is going on? Okay. So if you fix some round at some round t, okay, and let's say that like f bar t is just average flow so far up to time t. Just average the flow so far. And what we return is just f bar capital T, right? But anyway, now just from how we update the weights, we update the weight such that this thing is just x and this thing at time t. Like the weight at time t plus 1 is gonna be the weight from time t multiplied by this thing. This is the time t. Okay. Doesn't really matter, but like I just calculated for you. Like t is just t here is just the relative excess. But when you like multiply this all together and unfold it, you get that this thing at time t is just going to be the sum of relative excess. Okay. But if you look at this thing, what is this? This is just each of d is just like df I is just d minus f out fi out. Actually, yeah, right. Fi out, right? So this sum is just like you can write it like this. Okay. Just some calculation, doesn't matter, you can verify this. But the point is that the weight of each node, it's just some exponential function that depends on this thing. This is like, and you can like, wait. Yeah. Think of this first. Like this is just the average excess of the node at time up to time t. Right? This is, what is this thing? Yeah. This is just excess of V average up to day t. So if the excess is big so far, then the weight is big. If it's small, if it's small, then this is small. But if actually it's really negative, then this is going to be big. Okay. And how do we like how do we define the potential? Is this thing minus this. And if I forget all the scaling thing, then you can kind of see that the potential of each node looks like this thing. So it means that like when this is positive, it just grow up exponentially. When it is negative, it just go down like exponentially. You see, like it's like it changed in the drastic way. So it kind of, yeah. So when this average excess is positive, it goes up exponentially fast, and when this is negative, it goes down negatively exponentially fast. And what do? In each round, every edge just send flow at full capacity from higher to lower potential. So when there's some guy with excess, it's just gonna try to send flow out of itself, like very quickly. If I have deficit, I'm gonna try to receive flow. So it just try to fix this thing. So at the end, you kind of expect that the deficit on each node should be kind of close to 0, right? That's the intuition. So that's important, and yeah, is there a question about this? Okay. So if it has excess, this thing is big, try to send flow out. If it has deficit, this is going to be small really fast, and it's going to try to get flow into it. So at the end, you hope that like this thing should be kind of the deficit, the residual demand at V should be kind of close to 0. And if it's actually 0, then we are actually done. We route everything, but it's not going to be exactly 0. How exactly, we're going to see now. Okay, so to make this precise, we're going to basically now, we're going to use weight update. We're going to, like, you're going to see that like this algorithm just kind of simulate weight update from like what happened in weight update algorithm. Okay. So the stock or the indices, the set of indices is just going to be, for each node, you have plus or minus. Okay. That's why like we have the weight W plus and W, the weight W for node U minus. In the beginning, this weight is just all 1. And the gain vector, we're gonna create the gain. The gain for the gain U plus is just the relative excess of U at time t, and the gain U minus is negative of that. Okay. And now, yeah, like this is going to be the gain, and it's the same gain in the weight update algorithm. And what we need to show is that, like, okay. What we show is that like this gain has small width, like just like in weight update algorithm. I need that this thing is not too big. It's going to be at most 2. Okay. And then we're going to see that we update the weights just like how we do it in weight update algorithm. That is, we're going to, the way that the weight is updated is just going to be like, okay. Let's do step by step. I'm gonna bound this thing, and I'm gonna say that the weight is updated in the same way, and at the end, the guarantee of the weight update algorithm will imply that the flow, our flow, is like can be routed with low congestion. Like the residual demand can be routed with low congestion, just from weight update. Okay, we're just gonna do this. Let's do it one by one. So yeah. So first, let's see that the relative excess is the most 2. if this is true, like the positive value of absolute value of RUT is at most 2. So it means that this is at most 2. So why is that? Well, okay. Let's consider this one, the residual demand. The residual demand is just this minus this one. I'm just gonna say that the absolute value of each of this is at most degree. Okay. So first, this one is at most degree because this is what we do in the first step. Okay. This one is at most degree. That's clear. Like the flow out of each node is at most degree because we send flow at full capacity, not exceed the capacity. Okay. So this one, the absolute value of this one is at most 2 degree, which means that R, which is just this one over this, is most 2. Okay. So that's first thing. The width is actually just 2 at most. I call this thing the width. Okay. And now, if we set W to be 2, the omega here to be 2, then the way that we update the weights is just precisely like in the weight update algorithm, because what we do, right, we say that T plus is just UT plus, actually this is alpha, sorry. Alpha 2, and this is R, U, T. And similar things for minus. So it's just this, and this is exactly the same rule in weight update. Okay. 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 Are we good? Is it clear so far? This is how we do in weight update, right? You just need to update the weights like this. And I just do the same thing here. Okay. Okay, so like, and now the last thing is that, okay. I claim that this is exactly this one. Okay. So note that in the weight update algorithm, we kind of look at PT, inner product with GT, but PT is just the same as WT. Like this thing is just the same as scaled down by the sum of W. Right? So, yeah. So far, like I just claim that this thing is something that we look at in the weight update algorithm, and it has like a really tight relationship with like, and this thing is essentially this thing by scaling, and this thing has something to do with what appears in our algorithm. This is exactly what we check in the algorithm, whether it's less than 0 or not. Okay. Okay. And we can verify this just by calculation. So like the inner product between these two, we just sum over all indices J, this thing. And this is, but this one is like to sum over all nodes. And like for the plus part, we get this one. The minus part, we get this one because GU minus is negative of this thing. Okay. And then I just rearrange. I move R out, and I get this. But R is what? R is just relative excess, which is excess over degree. But what is this? This thing is just a potential of U. So this is just inner product between potential and the excess. Okay. Okay. So now I'm gonna conclude. Okay. So if the algorithm return the flow, then I'm gonna claim that the residual demand or excess respect this one, which means that the residual demand is routable in this expander with congestion phi epsilon. We want to prove this. Okay. So consider this G star, okay, which is the average gain. Okay. This average gain, I can just write down as like G star at U plus. It's just sum of this thing. But this is just relative excess, which is, yeah, it's just this one. Okay. And now this one, the sum, this is average of the excess. It's just the same as the excess of average flow. F is our flow, which is average flow. This is average of the excess per round. It's just the same as average of, like the excess of average flow. Okay. Okay. And for the minus, this is minus here. Okay. But what do we know? We know that if algorithm return F, then this one is always at most 0. This is like, because if it's non-zero, then we would like do a fire cut, remember? Yeah. So this one is at most 0 for every round, T. But this one, we just show that it's just the same thing as this one, which is kind of, this just means that, it's at most 0, right? Because this is just it's a scaling of this one. So it means our average gain, like our gain per day, is at most 0. But if what we gain per day is at most 0, then weight update guarantee says that G star, which is like the average gain of every stock, of every index, is going to be at most 0 plus alpha for every J. This is a kind of average over all J according to this distribution for each day. It's not, doesn't really talk about every J, every index. But here, now after T days, then like this thing is at most alpha. Okay. So what does it mean? It means that this one is at most alpha. This one is at most alpha. So it just means that we get this, and it means that the F here is at most alpha times degree. But that alpha is epsilon phi. So this just means that df, the excess here, respect epsilon phi times degree. Okay. So quite a lot of calculation, but like the way that you should think about it is just that like you just apply weight updates. And the algorithm actually just like if you interpret it, it's just do the natural thing. Like be greedy on each route, be greedy. Send flow from higher to potential from higher to potential vertices. Be greedy on each round. Why does that make sense? Because the potential kind of keep track of whether you have excess or you have deficit, right? And then you just try to send flow from the excess to deficit in the greedy way. Like kind of don't even think. Then just average all of them per round. Then it's good. That's like it turns out. The power of saying that like you being greedy, be greedy per round, and then after each round you can average them and you are good on every node. There is no excess or deficit too much on every node. That's the power of weight update. Okay. Right. And now let me finish with sweep cut. Okay. This is when this thing is more than 0 and we're gonna find a violating cut. Okay, so what's going on here? When this is more than 0, it means that I claim that this is the case. Why so? Because like the residual demand or excess is just demand minus the flow out. So this is just the same as this thing. But if this is more than 0, then this part is less than this part. Okay. Now let's analyze this one. What is this? This is like, I claim that this thing is just the same thing as the sum over all edges. And look at the capacity of edge multiplied by the difference between potential. Why is that the case? Well, like if you look at it, when you look, let's say that the node U is at this level. Yeah, this is potential of U and potential of V. Okay. How does, if you look at each edge here, this edge, how does it contribute to this one? An edge will contribute like plus CE times phi V and minus CE times phi U. Right, because this edge, the edge from U to V, have like positive contribution to flow out of V. Negative contribution to U out because it go into U. And then like when you have and then you scale it up by phi because it's the inner product. Okay. So each edge contributes this much minus this. Make sense? So an edge E just contribute CE multiplied by the difference between the potential. That's it. Make sense? Questions? Yeah. So this is the place why we construct our flow like we did, like be greedy like we did. Okay. If we actually like send flow from lower to higher potential, then like this might give you negative value, but we always send from higher to lower one, so it's always like a positive. Okay. And we also send at full capacity, so this is just the capacity of an edge. Okay. And now, okay. And now my claim is that if this is the case, this is like if there is any phi such that this sum is smaller than this, like then you can actually find a threshold cut such that it's a violating cut. So yeah, this is where it's kind of similar to the flow cut gap thing, where we find a threshold cut. Right. So the idea is that I just gonna sort vertices into like sort vertices V1, Vn according to its potential, and I'm gonna claim that like one of this cut, one of the cut, like one of this prefix cut or suffix cut will be the violating cut. Okay. And this makes sense intuitively because yeah, like intuitively like you have that this thing is big, so kind of the demand is kind of big, and so like if the demand is big, then there should be some part where like the total demand inside the cut is bigger than the cut size. I will actually prove this formally tomorrow. Yeah. And we're gonna finish. If we prove this, we finish expander case. And then you're gonna see that to generalize to general graph, just by using tree flow specifier, it just generalizes it like immediately. Okay, so we see this tomorrow.